I'm here to talk to you about Tekla Labs, which is an all-volunteer organization. All of us are students at UC Berkeley and UCSF in a variety of disciplines, neuroscientists, I'm a bioengineer, mechanical engineers, computer scientists, and the fundamental problem that we're trying to solve, as Margot mentioned, is that there is an unequal access to scientific equipment, which is a big barrier to entry, not only for people in developing countries who are trying to do legitimate science, but also for educators, for hobbyists trying to set up do-it-yourself science labs. And the approach that we're taking to do that is to create a network of people who are either interested in using homemade scientific equipment or people who are interested in building, so designers, makers, and on the other side, educators and scientists. And from my perspective, our philosophy is based on two fundamental principles. And the first is that everybody can be a maker. So in traditional science, I believe the word I should use here is day science, we are very focused in on our own specialties. There's this perception that what you should do is everything that you have experience and knowledge in, and you should leave everything else to somebody who has more experience in that field. So in my undergraduate research, I worked in a biology lab. And among biologists, you want repeatability first and foremost in your experiments. So what you want out of equipment is something that you don't have to think about at all. It's going to do exactly what you know it's going to do every time, and you don't want to have to think about what's inside the black box. You just want to know, like, if I put my PCR in this thermocycler, it'll do the same thing and my PCR will come out. And what that's resulted in is scientific equipment manufacturers selling to large labs that can sell a very simple device like a magnetic stirrer with a hot plate. Just incredibly simple from an engineering perspective. It's just a heating element on top of a spinning magnet for hundreds of dollars. Whereas you can build something, as I'll show you, build that device specifically for around $30. But the reason why I think that the perception that you should just focus on what you know is flawed is that, first of all, not everybody has that option. As I mentioned before, many labs or individuals can't spend $350 on a basic piece of equipment like that, let alone thousands of dollars on something like a thermocycler. But also, some of my best educational experiences have come from building, have come from trying to put something together that I didn't know how to do beforehand. So building these devices, understanding the equipment that you're using, is not only going to allow for people to have more access to equipment, but it's going to allow for people to do better science. Even if there is an alternative to purchase the equipment, understanding the thing that you're using can help you do better science. But of course, you need the expertise in order to build something that's actually going to work. And that's where the second principle comes in, which is to learn from the experience of other people. There are a few critical pieces of knowledge that you need in order to successfully build a piece of equipment. There are safety concerns, obviously. If you're working with electronics and you don't have experience in electronics, it can turn bad really quickly. But there's also things like understanding what kind of technical specifications you need to fulfill. And even as a scientist who works with equipment, oftentimes you won't actually understand what it is that you need to design for. Stuff like temperature tolerance. If you set your hot plate at 80 degrees Celsius, what is the actual range of temperatures that that's going to experience? And these are things that knowledge of those factors comes from the experience of using the equipment and the experience of designing the equipment. So for everybody to be able to make their equipment, there needs to be detailed information available from those who have experience in design and in engineering. So in order to fulfill this need for people, what Tekla Labs is aiming to do is to create an online infrastructure platform for there to be a dialogue between users and makers. And the basic model for this is that we're going to try to have some standard verification protocols. We're going to have high standards for the types of information that are provided in these design documents, such as use cases, technical specifications, and safety information. So many of you are probably familiar with Instructables, the platform Instructables. It's like a DIY online, everybody submits their own recipes to do all kinds of different things. The problem with Instructables for an application like this is that there aren't really standards for what can be posted on Instructables. So Instructables has some great stuff on there, but there are varying levels of detail. And if you're looking for something that can actually be used in science, it needs to be standardized. You need to be able to say, I use this kind of equipment for this procedure, and if you want to repeat it, you can use something with the same specifications. So that's really the core of what we're trying to do here. In order to do that, we have a multi-step process. The first step is to assess the needs of the community that we're trying to design these devices for. So surveys that go out to scientific communities where they talk about what they need, and then we use that to provide a challenge for just the general maker community online. We've been doing that through competitions. So we've had a few competitions so far. We'll probably continue to host competitions. So the decision in terms of designs has sort of been to crowdsource the designs in order to get a pool of designs going that can then be added to by an evolving community. And then we test the devices and edit the recipes at Berkeley on site. And that's most of what we do, is that and the web design. And then finally, we provide the designs to the users. But there's one more step here that I'm missing. And that is that after we have provided the designs on the users, these are to the users, these are designs that have been built by somebody else, probably somebody who has a lot of engineering experience in a developed country and is maybe unfamiliar with the particular application that the user is trying to use their device for. So there has to be a feedback step. And the feedback step is where the collaborative online infrastructure comes in. Because once somebody has built somebody else's design, has found problems with it, understands more about the technical specifications that they're trying to build it for, they themselves can become a designer. The idea that designers and users are separate pools of people is kind of antithetical to what we're trying to do. So hopefully, and we haven't quite evolved our website to the point where this is happening to a large degree yet, but hopefully what we eventually get is people on the ground, people in South America who are trying to build labs with maybe not the same access to supply chains that people in the United States or Europe have, try these designs out, find there's something they can change, provide feedback, and modify the design, and then we have this evolving design that can work with modifications in a variety of situations. So back to the assessment. This is a survey that we conducted in Argentina and Peru. And the red here represents the proportion of people who responded who need access to that piece of equipment. And the green represents the portion of people who said that given a step-by-step guide on how to build the equipment, they would be interested in trying to build it. So something that was really exciting here is that you can already see that a large proportion of the people who said they needed the equipment would be willing to actually build the equipment. So these are people who were initially users who would eventually hopefully become part of our designer community. And in fact, something I found funny is here, if you look at the media rotator, the people who said they would want to build it is actually a higher proportion than the people who actually need it. So you've got people who are just like, oh yeah, cool, I want to build this thing, which is great. So after we've done that, we have hosted several competitions, like I said. The first one was Print My Lab, which was focused on 3D printable solutions. A lot of cool lab hacks here. My favorite is probably the computer fan centrifuge. You just stick that on a computer fan, turn it on. There's a lot of other really interesting things here. A micro manipulator. These tube holders are surprisingly expensive. Any of you who've worked in a chemistry biology lab know those little tube racks. Those are actually $50, $60, even though it's just a chunk of plastic. But we decided as an organization not to focus too much on 3D printing. And the major reason for that, apart from the fact that stuff like Thingiverse, there's 3D printing libraries all over the internet right now. But 3D printing has its own inherent barrier to entry, which is that you need access to a 3D printer. So if you're saying to somebody in Peru, oh, hey, cool, you can build your own lab, but first you also have to have this expensive piece of equipment, that isn't really going to work out. So for our next contest, we decided to focus more generally, and this was by far our most successful contest so far. It was the Build My Lab contest. We did it in collaboration with Instructables because they have this great infrastructure already for running contests. And we just decided to set really broad focus on lab hacks and lab equipment. And here we have a few. We have a CNC mill. That's a sterile tissue culture hood, laminar flow hood. This is a pH meter for water quality and a gel electrophoresis box over there. If you want to see, there's a lot of impressive projects. The URL right down there, instructables.com/contest/buildmylab. So the winning entries in this contest, we judged according to the principles that I was talking about earlier in terms of clear technical documentation. So the grand prize was this programmable hot plate. Now, a hot plate is a very simple piece of equipment. So this was not the most technically complex thing that somebody built. That wasn't how we judged this competition. The reason it won was because of the documentation that she provided, which was not only very detailed manual on how to build and program the device, but also characterization. So she actually did a finite element solution. That's that colored 2D map down there, showing the distribution of the heat on the top of the platform based on where the heating rods are connected. And then over there is a diagram showing the feedback algorithm and showing the temporal variation in the heating. So a scientist who wants to use this device and understands how homogeneous they need their heating to be, understands first of all, whether this device is suitable for their application and can quantify exactly how much the variation is going to be. So these are specs that you can put in your paper and say that, okay, we held this at 80 degrees C plus or minus 2 degrees for however long. And this is one of the first prizes. And the reason this was impressive is because this person provided a detailed experimental protocol for doing a melting point measurement. So they provide the device, and then they say, okay, well, if you want to use this in your lab, you don't need to figure out how to use this equipment. If you have no experience with this type of equipment, we'll provide you with exactly the recipe. And there's a picture from the protocol down here, but I encourage you to go on the website, the Instructables page, or there's a link from our own website, and read through this stuff because it's amazingly detailed, some of the information that was provided here. So then the next step is to test the designs on site at Berkeley. And so far, this is the bottleneck because, like I said, we're all volunteers. We're all PhD students. We all have our own projects. But we all like tinkering, like building. So this is the fun part, too. We've tested these two designs. These are actually designs that predate the competition. One of these was designed by undergraduate students at Berkeley, the media sample rotator. And then we have this magnetic stirrer that was designed by a collaborator, Malcolm Watts, at Massey University in New Zealand. So we validated these designs, made sure they work as intended, made some modifications to the design documents, and they're currently hosted on our website. And then, so in addition to this basic workflow, we're just sort of generally interested in global health and in providing sort of maker-based solutions to global health. So in collaboration with SEND, which is the Center for Emerging and Neglected Diseases at UC Berkeley, and with the Blum Center for Developing Economies, we hosted this hack day for global health. We had a lot of people from a lot of backgrounds, doctors, biologists, engineers turn out, and we saw some really interesting projects. So that one is the winning project. It's a bug zapper for malarial mosquitoes, which has a Wi-Fi chip in there. So it actually uploads data on the distribution of the mosquito population as it kills them off. So it allows for diagnostics and reduces the population at the same time. And then we also had this other project. These are 2 out of the 5 groups. And we had this other project, which was a spirometer, which is a device designed for measuring lung volume. So for pneumonia, for other diseases that affect your lung health. We had this device, I think they calculated it would end up costing about $2 for a reusable device with and then like 30 cents per test, as you'd slot out the tests and replace them. So this was a really exciting event, some of the other work we do. And I have a time-lapse video of that here, just to show you the activity. Maybe you can't see it super well because of the lighting. But a lot of people doing... Full screen. Oh, yeah. Oops. There we go. You can see the bug zapper coming together in the front here. But it was over 24 hours, and we got some really cool prototypes. So So that was an exciting event. And we periodically host those kinds of things because so far we're really just trying to focus on building that community of designers, getting people to come forward with cool ideas. And finally, just going to show you our website here. So this is the model. It's based on this platform called iFixit, which was a competitor to Instructables back in the day. It's now defunct, but we use their technology for our web hosting so far. So you have this ability to do feedback, to ask questions, to submit your own guides. There's a system where you can log on and you can submit designs and you can provide feedback. You have documents that you can switch between and sort of step-by-step documentation here, and then comments at the bottom. So we're probably going to improve on this design for our website because since we originally designed this, there's sort of been, HTML5 came out since this, and there's been a revolution really in online collaborative things like Google Docs. But for now, it's pretty workable, and that's definitely something we're going to do moving forward is a redesign of our website to make that basic collaborative infrastructure a little more functional. But yeah, so that's about it. I'd like to thank our Berkeley partners, Blum Center, Citrus, and Send, who I already mentioned, and then Clinton Global Initiative and Big Ideas at Berkeley, and the Berkeley Graduate Assembly for funding us. And of course, my fellow Tekla Labs members. And if you have any questions, I'd love to take them, or you can contact me. My email's right there, or visit our website. Thank you.